Welcome. In this session, we will be discussing how to build a bland enrollment plot. We already have got the dataset heme loaded onto EZR. We can check out what are the variables and what are the descriptives. And these are the descriptives over here for the capillary method of estimation by the two HemoQ devices, by the reference method, and the venous uh, estimation by the two HemoQ devices. Now, before proceeding any further, for checking the error, we should have to know what the acceptable error is. According to one of the methods, internationally accepted uh, percentage for error is 7% for hemoglobin, as given by CLIA. So, what is 7% for of hemoglobin? Which hemoglobin value should we take? The critical value of hemoglobin. In the case of blood bank donors, the critical value should be 12.5 because 12.5 is the cutoff point for selection of blood donors. So let us calculate 7% of 12.5, 0.07 into 12.5 is 0.875. So our acceptable error for hemoglobin, the maximum acceptable error should be 0.875. We have to know that these are the acceptable ranges. Anything, the values between the instrument and the reference generally should be between plus 0.875 to minus 0.875. How do we draw the Bland-Wallman plot? Bland-Wallman plot is just a scatter plot of the differences versus the average. So we have to create variables of the differences. Now we get to variable, create new variable. Let us call it differences. Cap1 diff. Okay, and this should be the method we are trying to compare minus the reference method. We do this, we have created one variable known as cap1 diff. The next thing we should be creating is a variable of averages. Again, go to variables, create new variable, and we need the averages. Average of the method and the reference, the average of the two methods. Average cap1 ref. Let's put it. We can put any name we like. Let us do this. Cap1. What is the expression? Plus ref, and the average would be divided by 2. So we have made another new variable, average cap1 ref. What this is it is just a scatter plot. We take out these choices where the x-axis is the average and the y-axis is the difference between the two methods. We click OK. This is the basic thing of a Bland-Wallman plot. However, we have to add two more lines. What are the two more lines? The two more lines are the three more lines actually. One is the mean difference. What is the mean difference? We can always get it by the numerical summaries. Let us see the cap1 diff. Okay, the mean difference is minus 0.5280702. So we have to draw this. There's a simple command in R which is AB line, then H is equal to minus 0.52800702. The actual difference, we get that. Here is the mean difference which has been drawn. Now we have to draw the upper limit and lower limit. The upper limit and lower limit are nothing but mean plus 1.96 of the standard deviation of the differences, mean minus 1.96 of the standard deviation of the differences. So what is the standard deviation? 0.752318. Let us have this minus, let's see what is the upper limit going to be. This 0.5280702, okay, minus 1.96 into the standard deviation 0.752313189. What is this? Minus 2.002615, and the other thing will be plus this, plus 1.9660 is 0.9464. So let us draw these two lines additionally. It's very easy to add lines to plots in R. We have got the lower limit, and then we can always add the upper limit as well. The upper limit was 0.94. We add another horizontal line. H is equal to 0.9464748. And we have got this. This entire thing is what is known as the Bland-Altman plot. In the Bland-Altman plot, we have this difference of the two methods. This is also known as the bias. Over here, it is negative. This means that capillary 1 was usually lesser than the reference method, usually gave on the average gave a lesser value than the reference method of Sysmex, and mean plus 1.96 ST of the difference minus 1.96 ST of the difference. That means 95% of the values should approximately lie within these bounds. We should examine the graph and see whether these differences are actually distributed uniformly throughout. In this graph, they seem to be distributed uniformly. If they are not distributed uniformly, then maybe we need to do some transformation to make them get distributed evenly. Now, the thing about Bland-Altman plots are that you may need to draw the confidence intervals of the upper limits and confidence intervals of the lower limits. Looking at this Bland-Altman plot itself, we can get to know that possibly the method is not accurate enough because the upper limit of agreement is greater than 0.875. It was 0.94. As we see over here, it was 0.94. So it is greater than the upper limit is greater than the maximum acceptable error. The lower limit is also lower than minus 0.875. So overall, the accuracy is not acceptable. However, for other methods, we may need the confidence intervals to get a greater idea of whether the limits of agreement are acceptable or not. However, in ECR, there is no way to get the confidence intervals through the menu very easily. So we need to install an additional package. For that, we need to go to the R console, click on packages, click install packages. There are crayon mirrors. We select the default, and there's a package known as blandr that we are going to install. So let's see over here about Blender. There are plenty of packages in R that contributes to the charm of R, but it becomes very difficult and confusing at times. The Blender, we have found Blender over here. We click OK, and this will get installed very easily. Here, that has been installed. Now we have to load this package. Once installed, it stays over there in R. You do not have to reinstall it again and again. Now we load the package. Library, just remember the spelling, library Blender. Now we have to make use of the command line. Don't be afraid, it's very easy and there are very simple commands for this. The command is blender draw. Blender dot draw. Then method 1, method 2. What is the method 1? The method 1 is cap1. Method 2 is ref. How do we put them? Method 1 is for any command we do the data set, dollar, the name of the variable, cap1 representing the method 1, the name of data set heme, dollar, name of the method 2. Over here it is ref. And we do this and we get the bland Allman plot for comparison of two methods with the confidence intervals. This represents the bias, the difference with the confidence intervals shaded in blue over here. This line represents the upper limit of agreement, upper 95% limit of agreement, with again this green shading shows the 95% confidence intervals of the upper limit. This line over here shows the lower 95% limit of agreement, and this shading in pink is the confidence interval for the lower limit. For a method to be accurate, this entire thing, this upper confidence interval of the upper limit and lower confidence interval of the lower limit, they need to be within the acceptable error limits. However, over here, our acceptable error limit was 0.875. Both the upper limit and the lower limit are outside the acceptable error limits. Hence, capillary method should be taken to have unacceptable accuracy as far as CLIA standards. Let us see how a acceptable accuracy would look like. Let us take the example of mean 1, venous measurement on HemoCube 1. Let us draw this. Use the same command blender draw. Venous measurement was Veen 1, and here it is. The bias with the confidence intervals, the upper limit of agreement with confidence intervals, lower limit of agreement with confidence intervals. Over here, we can quite easily see that the lower limit of confidence interval is far within minus 0.875, which would have lain somewhat over here. What about the upper limit? We cannot be so sure. Maybe if we had the numerical data, it could have helped. For this, there's another easy command to see what the exact confidence intervals are. The command is blender dot output dot text, and we get the confidence intervals. This entire thing is being given, and we get the confidence intervals. For the upper limit of agreement, the upper confidence interval is 0.857, which is lesser than 0.875. The lower 95% confidence interval is, of course, would be lesser than that. For the lower limit of agreement, again, both the limits are above 0.875. Thereby, All the limits are within the interval of the acceptable error, for the measurement, 0.875. So the Venus method seems to have acceptable error. Hopefully, by the end of this session, you will be able to make bland Altman plots on your own. Thank you.